So I wanted to do a few more example problems of electron configurations. So we're going to do sulfur. Sulfur has 16 total electrons. It has atomic number of 16. So we can draw the orbital diagram. And this isn't drawn perfectly to scale. There should be a pretty big separation between 1s and 2s that I didn't draw exactly correctly. But if we're drawing in our electrons, we've got 2 in our 1s, 2 in our 2s, 1, 2, 3, 4, 5, 6 in 2p. So now we have a total of 10 electrons. 2 in 3s, that's 12, 13, 14, 15, 16. Okay, so this is our orbital diagram for our sulfur. So now we can draw out our electron configuration. So our full electron configuration is 1s2, 2s2, 2p6, 3s2, 3p4. Okay, so this is our total valence this is our total electron configuration. So our valence electrons are the ones with the highest principal quantum number. So our 3s2, 3p4 is our valence electrons. So we have 6 valence electrons. So remember that it's our valence electrons that we really care about. So we can often write what we call a condensed electron configuration, where we put the previous noble gas in brackets. So in this case, we're going to write neon 3s2, 3p4. So this is our condensed electron configuration. So that's going to be a really handy tool. So these are our valence electrons, and then these are our inner electrons. So our valence electrons are what actually participate in bonding. It's also important to note, so this is a figure from your book, from the OpenStax book, that shows electron configurations. And one thing I don't like about the electron configurations that they show in your book for the orbital diagrams is these are horizontal orbital diagrams. I like to draw vertical orbital diagrams so you can really see that the 2p is higher in energy than the 2s, which is higher in energy than the 1s orbital. But something I wanted to mention briefly is that half-filled orbitals are more stable because they allow electrons to completely spread out. Remember Hund's rule, we said that electrons spread out before they pair. So your nitrogen electron configuration is going to be a little bit more stable than this oxygen electron configuration, where you reintroduce some electron-electron repulsion by pairing this electron. But the most stable sublevel is our completely filled sublevel, and that's because we have very high effective nuclear charge, which pulls these electrons very tightly to the nucleus. Because half-filled sublevels and fully filled sublevels are slightly more stable, we see some pretty important exceptions to the Aufbau principle. Two important exceptions to the Aufbau principle are chromium and copper. If we were to write the condensed electron configuration for chromium, we would say that it's argon, 4s2, 3d, 1, 2, 3, 4. But because it's better to have a half-filled sublevel than a partially filled sublevel, the actual electron configuration for chromium is argon, 4s1, 3d5. So this is an important exception to the Aufbau principle. Copper is also an exception because it wants to have that fully filled sublevel. So for copper, the correct electron configuration is argon, 4s1, 3d10, rather than 4s2, 3d9 like you would normally predict, so that it has this completely filled sublevel or a half-filled sublevel. So chromium and copper are important exceptions to the Aufbau principle.